Okay, good morning. Last time we finished up looking at rotational dynamics, which was looking at the dynamics of an object going around or spinning in a circle, or an object that was rotating. What we're going to do today is take a look at a motion that initially is going to seem very, very different, but we will see has some very, very important similarities to rotational motion. This brings us to section 10. Which is entitled Simple Harmonic Motion. And elasticity. So first, let's imagine that we are looking at a spring. So here's a spring. And let's look at the force exerted by the spring. So we're going to apply a force on this spring and see what kind of force the spring exerts. Now, so that we can ignore kind of the gravitational force, let's imagine that this spring is horizontal and we're pulling on it sideways. So we can ignore kind of the vertical forces due to gravity. Okay, so here we go. Here's our spring here. We're going to assume that it's attached rigidly to one side. And we'll assume that there's some object, maybe a mass or something like that, over here. Now, let's imagine that we displace the mass from the equilibrium position. So the equilibrium position is kind of the position that the spring would take if there were no force acting on it. So we displace the object to one side, over here, some displacement x. The spring, we'll then assume, pulls back to the left. So if we displace it to the right, the spring pulls to the left, with some force F. Likewise, we're going to assume that if we compress the spring, so that if we displace the object to the left, we end up with a force pushing back to the right. So let's notice that the force is always in the opposite direction to the displacement. Now, we'll come back to this in just a second, but let me emphasize that the force we're talking about is not the force that we apply with our hand. Obviously, to pull this thing over here, we would have to pull the mass to the right. So the force that we apply would be in the same direction as the displacement. That's not the force I'm talking about. The force we want to look at is the force that's actually being exerted by the spring on the mass. So if we displace the mass to the right, the spring pulls back to the left. If we compress the mass to the left, the spring pushes back on the mass to the right. Okay, so let's look at the force exerted by the spring. So in one dimension, we have that the force that is exerted by the spring increases as we increase the displacement. The more displacement we apply, the more the spring pulls back. Now, obviously, we're going to get to a point where if we pull this too much, we'll end up breaking the spring or something like that, or we'll end up actually distorting the spring so much that it bends the metal permanently, and actually you can see that that's what happened to some extent to this spring. So we end up distorting the spring more than it really can stand. Now let's assume that we don't do that. Assuming that we don't displace it too much, either extension or compression, we'll make an approximation. We will say that the force is actually proportional to the displacement. To make this an equality, we will stick in a constant of proportionality, k, and I'll define k in just a second. And then to emphasize that the force is always in the opposite direction to the displacement, we'll put in a minus sign. So we've got the relationship between the force being applied by the spring and the displacement, F equals minus kx. Now this is a very, very important result. This is called Hooke's law. Hooke was actually a contemporary of Isaac Newton. And this relationship describes what we will refer to as an ideal spring. Real springs might have a more complicated relationship between the force and the displacement, but we'll assume that the spring that we have is an ideal or perfect spring, so that we will assume that they are exactly proportional to each other, F equals minus kx. K is called the spring constant. And basically it tells us how strong the spring is. If we had a value, some large value for K, a small displacement would give rise to a big force. That would be like a spring that, if we tried to pull it a little bit, would give a big force pulling back. So that would be a very, very stiff or strong spring. A spring constant that was very small, we could give a large displacement to the spring and still have a relatively small force. So that would be like a spring that was very easy to stretch. I could just with a small force extend it a lot. So K basically tells us the strength of our spring. Small K, a weak spring. Large K, very strong or tight spring. The units of K, we can see from this equation, will be the units of force divided by the units of displacement. So the units of force are newtons. Units of displacement, meters. So the units of K will be newtons per meter. Now you could actually divide the meters out of newtons and write that as kilograms per second squared, but we'll just typically leave it as newtons per meter, which gives us a better idea of it being a force per distance. All right, so now let's imagine, let's go back to our picture. So here we go. Let's imagine that we extend the mass to one side. So say up here, we extend the end to one side, and then we release it. What's going to happen? Well, the spring is going to pull the mass back, and then it will push it back, pull it back, push it back. So the mass will oscillate back and forth and back and forth and back and forth. And if there's no friction, we'll assume that it just keeps going with a size of the oscillation that does not change. It just goes back and forth and back and forth. So let's look at this particular motion. Let's imagine that we could actually graph this motion as a function of time. What would that look like? So let's imagine we've got our oscillation like this. Our mass is going back and forth and back and forth. Imagine maybe we had a pen attached to it and we had some graph paper scrolling by. What would this oscillation look like? Well, it would look something like this. Up and down and up and down and up and down and up and down. It basically looks just like a cosine wave, something like that. It'll go up to a maximum of some value and a minimum of some value that are actually the same distance from the equilibrium. We'll call this distance A, and we'll refer to that as the amplitude of the motion. So the amplitude is not the distance from maximum to minimum, but it's actually from equilibrium to maximum. So that's going to be our amplitude A of the motion. This particular kind of motion is called a simple harmonic. That object is a simple harmonic oscillator. The type of motion that it has is called simple harmonic motion. So we'll refer to the actual object as a simple harmonic oscillator, an SHO, while the motion is SHM, simple harmonic motion. All right, so let's remember A is what we will call the amplitude. The amplitude of the motion, and that is 1/2 the size of the motion, you might say, from the maximum displacement to the minimum displacement. So it's 1/2 of that overall distance. Okay, now, that simple harmonic motion, let's leave that for just a minute and let's go back to our uniform circular motion, just for a minute. Let's kind of completely forget this for a second and let's go back to what we had been talking about with uniform circular motion. let's imagine that we've got a mass on a spinning table, and this table, let's imagine, is going around in a circle like this. So our mass is going around and around in a circle. So if I could put this up sideways, the mass is basically going around in a circle like this. Uniform circular motion. However, rather than looking at it, say, from above, let's imagine that we're going to look at this right edge on, perfectly edge on. So we're just going to look at one dimension of the motion. We might imagine that we would, say, take a light and shine it on this thing and basically look at this as it goes around and around and just look at the shadow of the object. So the shadow would basically just be going back and forth just in one dimension. Rather than going around in a circle, we're only going to look at, say, the x component of that motion. What's that going to look like? Okay, so here's our mass on our table. The table is going around and around and around. Our mass is going around in a circle. But let's imagine that we only look at this from one dimension. We're only going to look at this, say, from the side. So we shine some lights on it and we imagine that we look at just the shadow of this thing as it goes around. And again, let's imagine that we could graph this motion. We've got some graph paper going by and we kind of graph the motion of the shadow. What's it going to look like? Well, it's going to look just like that. Something that looks, again, a lot like a cosine. Well, let's look at this quantitatively. What is this motion really going to look like? Well, let's imagine that we've got an object going around in a circle. Here we go. Here's our object going around in the circle. Here are our lights, so shining like this. So basically, we are just looking at the x motion of the object as it goes around in a circle. What is the x coordinate of our object? Well, let's imagine that we've got it going around in a circle, and we represent the angular position with theta. So wherever it is in the counterclockwise direction, we're going to measure that angle as theta. We'll assume that the radius of this circle is a, where a is the amplitude of the motion. Now why is that? That's going to give us an amplitude that is going back and forth a distance a to the right of the center and a distance a to the left of the center. So there we go. Here is our object undergoing uniform circular motion at some time t. It'll be at some position theta, and it's got some radius of the motion a. And let's assume that theta is actually 0 at t equals 0. So this will be our initial position, the initial position of the object as it's undergoing uniform circular motion. Okay, so here we go. Here is our object going around in a circle. And what we want to figure out is what is the x coordinate of our object. Well, for uniform circular motion, we know we've got the 4 rotational kinematic equations. So if we think about the third kinematic equation, we know that theta is going to be theta naught plus omega naught t plus 1/2 alpha t squared. Now this is, okay, so we know that we're starting off here at t equals 0. In other words, our initial angle theta naught is going to be 0. We know this is uniform circular motion, so there's no angular acceleration, so we know alpha is 0. And therefore, omega, the angular velocity, is a constant, so omega naught is going to be the same as omega at any time, and so we can actually remove the omega naught there, and what we end up with then is theta is equal to omega t. From our diagram, we see that x is equal to, now we've got a right triangle here, x is going to be a cos theta, or with theta equal omega t, we have x equals a cos omega t. And there we go. This tells us the position, the x coordinate of our object as a function of time in terms of the angular velocity omega and the amplitude of the motion a. So there's our position. Now if we go back to uniform circular motion, we can remember that omega was equal to 2 pi divided by the period, which basically told us the number of radians that the circular motion was rotating through per second. Let's define another quantity, f, which we'll think of as, rather than the angular velocity, we'll define f as the frequency, which basically tells us how many rotations per second is our circular motion going through. So the period tells us the number of seconds per rotation. F tells us the number of rotations per second. Well, F is basically just equal to 1 over t, 1 over the period. For example, if we have, let's say, a period of, let's imagine, 10 seconds, so that means it takes 10 seconds for 1 revolution, the frequency would be 1 divided by 10, or 0.1 inverse seconds. So that tells us that we get a frequency of 0.1 cycles per second. In other words, we're getting 0.1 rotations completed every second. 10 seconds per rotation, or 1/10 of a rotation per second. So we can see how these two are related to each other. Omega, which is 2 pi divided by the period, well, putting 1 over the period as the frequency, that is just 2 pi times the frequency. So the angular velocity we basically have is just 2 pi times the ordinary frequency, or in this case it would be 2 pi times 0.100 inverse seconds, or 2 pi is 2 times 3.14, 6.28, or 0.628 inverse seconds. Or, to emphasize that this is an angular velocity, we can write this as radians per second. Radians we can think of as a very natural kind of unit that we can kind of stick in there when necessary, but keep in mind it's emphasizing a phase or an angle of the motion. All right, so once we've got that, let's think about, we've got the position as a function of time. What is the velocity as a function of time? What is the velocity of this object as it's going around the circle? But what's the x component of the velocity? Rather than what's the velocity vector, what's just the x component? Because we only want just the one-dimensional part of this motion. All right, so here we go. Here's our object undergoing circular motion. This projector is distorting this a little bit, we just noticed, so it's not exactly a circle, it looks more like an ellipse, but just imagine this is just a circle. We've got our object undergoing uniform circular motion, which means the speed is uniform. In other words, the magnitude of the velocity vector is constant. But what we want to figure out is what is just the component of the velocity in the x direction. So if this is the tangential velocity, this is what has a uniform magnitude. We want to figure out what's the component of this in the x direction. So what we want is v here, the x component of vt, the tangential velocity. Now, let's imagine, again, our object is at some arbitrary angle theta. Well, we know this is horizontal, so we know this angle is theta. We know that this is tangential to the circle, which means it is perpendicular to the radius, which means this angle is 90 minus theta. This is theta, this is a right angle, this must be 90 minus theta, which means if this is a right angle, if that's 90 minus theta, this is theta. So, if this has a magnitude of v sub t, the magnitude of the tangential velocity, we have the magnitude of the component that we're looking for is going to be vt sine theta. So v equals vt sine theta. Okay, so here we go. What we have then is v, the component of the velocity that we're looking for, is equal to vt sine theta. But let's notice that in this position, the velocity is actually going to be in the negative direction. So we actually have to put in a minus sign here so that the velocity actually has a negative value. Well, let's keep in mind Vt is constant. The amplitude, or I should say the magnitude of the tangential velocity is constant. And we know from our uniform circular motion that that is equal to the radius of the motion times the angular velocity of the motion. The radius of our particular motion is the amplitude a. So we can write this as a omega. So we can write our velocity then as minus Vt, which is a omega, sine theta. But theta, remember from before, is just omega t. So we can write this as sine omega t. There we go. There is our velocity as a function of time for our uniform circular motion. V equals minus a omega sine omega t. Well, if you remember from before, we've got the position as a function of time. We have the velocity as a function of time. Well, what's next? What is the acceleration as a function of time? Let's see if we can't figure that out. Let's go back to our picture. Okay, here we go. So, now we're going to look at the acceleration. What kind of acceleration does an object undergoing uniform circular motion have? It has centripetal acceleration. So we know we've got an acceleration towards the center of the motion. So here's our centripetal acceleration. And let's remember, this is going to have a uniform magnitude. However, the direction of the centripetal acceleration is going to change constantly, always pointing toward the center of the circle. Again, what we want is the x component of this, and so we want this part of the acceleration right here. If this is theta, and this is towards the center, we know this is theta here. So the component that we want is going to be the magnitude a sub c cosine theta. So we are going to want our acceleration is ac cos theta. Okay, so what we want is this component of the acceleration right here. The centripetal acceleration points toward the center of the circle. We want the x component of that acceleration here, which is labeled a. And we know then that a is equal to, if this is theta and that's theta, we want a sub c cos theta. But again, notice that this component of the acceleration is in the negative direction, so we need to stick in a minus sign there. And let's remember, what is the magnitude of the centripetal acceleration? Remember, centripetal acceleration is v squared over r, but v, remember, is the tangential velocity, so this is going to be vt squared over r. The tangential velocity, remember, is r omega. So this is going to be r omega squared over r, or r squared over r is r omega squared, but remember the radius is a, and so this is a omega squared. So what do we have? The acceleration is minus a omega squared cos theta, and again, theta is omega t. And there we go. There is our acceleration as a function of time, the x component of the acceleration as a function of time, minus a omega squared cos omega t. So let's recap. What are all of the results that we have so far? Okay, so here we go. What we've got is the position, the velocity, and the acceleration as a function of time for our uniform circular motion, but let's keep in mind all of these are just giving us the x component of these quantities. So what we have is x is equal to a cos omega t, v is equal to minus a omega sine omega t, and a of t is equal to minus a omega squared cos omega t. Now, remember, this is for uniform circular motion. We started out talking about simple harmonic motion. What does this have to do with simple harmonic motion? Well, if you'll remember, we looked at uniform circular motion in one dimension, and it kind of looked like the same cosine type shape of the simple harmonic motion. But does this really have anything to do with simple harmonic motion? Does it describe that motion at all? Well, let's go back to Hooke's law and see what we find out.